Awesome, thank you. Good afternoon, everybody. My name is Darren Wood. I work in field engineering at Neo4j. I wanted to do a quick session this afternoon. We have limited time and I've got a lot of stuff to get through. But I just want to talk about using knowledge graphs in conjunction with language models to improve vector search. And then I have a little bit at the end on generative AI and general topics around that. I know you've already heard a lot about this at the conference. So I think something I'm going to do a little bit differently is, do a bit of an intro, talk about the power of knowledge graphs. There's also been some other excellent presentations today on knowledge graphs, so I'm sure everybody is well versed in the topic. But then I'm going to get into some practical examples, going to actually show you some code, show you some of the plugins and modules that we build at Neo4j to sort of help you get started and be successful with knowledge graphs and language models. So like I say, I work at Neo4j and I've been lucky enough to work with lots and lots of our wonderful customers on lots of popular graph use cases. And this is just sort of a selection of the kinds of things that we do with graph data at Neo4j. And so obviously, things like real-time recommendations, CBA uses us for IT and network operations and understanding vulnerabilities and failures in their IT systems, and lots of other really great use cases around identity and access management. They're really good use cases for using graphs to understand data better, and you really get some good outcomes in these sorts of cases. But today, of course, I'm going to talk about language models because at least half of the people we interact with these days want to talk something generative AI and language models. So super popular conversation to have. I thought I'd start with a quick audience poll. Who has actually worked on a project using LLMs, using language models? A good show of hands, it's getting better. And that can be anything. It can be like language models, doing generative AI, or even just, doing semantic search, vector search, using text embeddings and things like that. But yeah, when I started giving these kinds of presentations about 18 months ago, I think the people were kind of really at the very beginning of their journey. And so you can tell me if any of this, relates to you. In these sort of 1.0 type language model projects, we often saw, people being really aggressive with using language models directly, with the direct consumption of LLMs, getting an API key, writing 17 lines of code, putting something, into a POC in a few weeks. And I always found that, they reached a sort of certain maturity level, which is fine when we're doing things like, asking LLMs to write poems for us and things like that. Our expectations are set, very low, and, the results are really good, right? So we sort of have this, expectation that meets the reality. Unfortunately, with most business settings, our expectations are set much higher. And of course, we get this amazing success in the beginning in a very short amount of time, and we're very excited about it. But then we sort of start to see some of the issues, right, around these projects. And of course, then we sort of enter this kind of plateau phase, where we're sort of trying to take what we built initially and we're trying to improve on it, right? Get it to perform and meet our expectations. And so that involves a lot of different activities, and usually they're kind of longer time frames, right? So our stakeholders and our sponsors, they sort of said, hey, you said this was going to take a few weeks, but now we're kind of in this plateau where we're sort of doing different model selection and we're sort of trying to do some fine tuning. We might be parameter tweaking and things like that, but we're actually not quickly accelerating towards our goals like we were in the beginning. And so again, things like RAG can be introduced to, improve the performance of these applications. But they themselves introduce other issues, right? So if we do fine tuning, we run into issues like security, right? So if I'm going to put some of my data, my actual organizational data, into a language model with fine tuning, now who am I going to expose that to later on? How do I control access to that? So some of these solutions actually cause problems in themselves. And then quite often, if we're training models based on data sets that we have around the organization, There are relationships in that data set, but they're not seen by the model, right? So you might have like identifiers or something in those data sets, but we train the models with them, but they don't realize that the identifiers create a connection between things because they just have a semantic understanding. They only understand language and terms. They don't really understand structure or connections in your data. And so a lot of projects that we've seen run, these sort of like early language model projects, they kind of end on this sort of plateau, right? Like where it didn't really meet expectations and you know, they were unable to accelerate towards those goals. And so we think this is the opportunity with knowledge graphs, you know, by taking that same data that perhaps you tried to do fine tuning or you tried to do some, you know, basic vector-based RAG or something with, take that same knowledge that you have, same information that you have from your organizational data sets, connect them together in a graph, and then ground the language model with graph. And so why knowledge graphs? Well, knowledge graphs are fantastic, like I said, for all of the use cases that I showed on the first slide. But you know, one of the great things about knowledge graphs is that you probably already have the data that powers them, right? So we've been working with lots of organizations that have their data, but it's actually all siloed, right? And so even people using enterprise data warehouses, in fact, I was in a meeting with a retailer 2 weeks ago, and they said, yes, we have everything in one place, but it's not connected at all. Like it's completely siloed. We have no way of using it together. So yes, we have this big data warehouse, but it's just basically these silos of data. And data like this, like customer data, we have our product data set and our product catalog, you know, in another silo. We have event data like customers' interactions with our website, the offers that they're subscribing to, things like that. That's all like in our rewards program site, and it's all siloed off up there. And then we have third-party data like click data and things like that. And of course, you can keep going, right? So like if we have products, then we have a supply chain, we have stock levels, we have all kinds of information. And if you take all of this and create a knowledge graph from it by connecting these things, because all these things are related. Products are related to your supply chain, customers purchase products, customers are interacting with offers in your rewards programs, things like that. We can get a really rich, like really nice high resolution picture of what a customer is to your organization. And so we have this sort of structured data now that we've taken and sewed together into a knowledge graph. But of course, one of the things that language models allows us to do is introduce unstructured data as well. And graphs are really good for connecting unstructured data into your structured data as well. And so if we take like unstructured data, like, you know, maybe we're an insurance company and we have policy documents or PDSs, like descriptions of the policies. If we're a retailer and we have products which have, you know, product descriptions and things like that, we can take that unstructured data and, you know, there's sort of two ways to integrate unstructured data into a graph. Like one is by taking that unstructured data and seeing what it's directly related to. So obviously if we have a product, right, there is structure in our graph for the product. We can take the piece of data we have about it, chunk it up, you know, make some text embeddings for it. And then if we do a query or we have a customer ask a question or search for a product or something like that, that will get us into a chunk of the document. It'll go up and it will enter our structured data set via the node that corresponds to it. And so that's one way of creating a path from unstructured data into a structured data set to improve the results of semantic search through the process of retrieval augmented generation, where we grab like additional context from, you know, looking at the graph that's sitting behind the unstructured data set. And then another use case for using language models with graphs is actually pointing at some of these you know, chunks of your unstructured data and extracting information from them that directly relates to the rest of your graph model. And so this example here that I've got pictured, it actually comes from an insurance company use case, you know, whereas insurance products are really complex, right? So you have like, you know, for an item of clothing or something, it's pretty straightforward. You just have a, you know, text description of it and that's your unstructured data about it. But for an insurance policy, you have like this big PDS that has lots of different options and things like that. And so that's actually not as straightforward. If I ask, for example, does my insurance policy cover flood or something like that? there are lots of different options in insurance policies. Some you have to opt into, some they only cover flood for certain reasons or certain types of events. And so there's this really rich structure inside that policy, which is described in a PDS in an unstructured form. But if we show the language model the structure that we're trying to pull out, like as part of connecting into things like options in the graph or a feature of a product, and we pass like pieces of that unstructured data to it, we can actually connect it directly into the graph. So essentially, we're pulling structured data from the unstructured data and directly connecting it into the graph. And so then I can start to answer questions like, if a customer asks, am I covered for flood insurance? Well, first of all, I can check that, the PDS that I've retrieved, the chunk of as part of the semantic search is connected to a product that the customer actually owns, right? So that's context. And then I can see if the customer actually has that option for it. And then I can answer the question in a much more concise way, right? Whereas usually the result of this kind of question would be, well, this kind of product does have that as an option, but you will need to check if you have the option or not. So I think this is a really good example of where we can use graphs in conjunction with this unstructured data to answer questions that are much more targeted to the user or the asker of the question. And so we're not really the only ones that think that knowledge graphs are important to Gen AI. Obviously, there are industry, bodies like Gartner that see knowledge graphs as basically in the bullseye of the impact radar for Gen AI. And so they're, very much front and foremost in this area. And I think this is one that's probably lesser known, but even at like a query language level, the GQL query language has just been ISO standardized. And so if you look at the history of database query languages, this is the first new query language in 40 years. Right? So it's the first ISO standard query language in 40 years. So this just happened this year. A lot of people aren't aware of this, but I think this is real validation of knowledge graphs and the powerful, or the use of knowledge graphs in these types of applications. Okay, so I promised some actual examples. So as I was saying before, why does traditional RAG sort of fall short, right? And why can we help with knowledge graphs? So of course, one of the problems which I've already spoken about is they only leverage a fraction of your data. So if you're using your unstructured data set, you're creating embeddings, you're doing search that gets you to an embedding, you're actually only using that unstructured piece of your data set. You're not going into structured data that you have that you can connect into that larger knowledge graph. So you can miss this critical context. So that simple example where I talked about that customer from an insurance company, if they ask a question about, a policy or the features of a policy, then we should be checking that they're actually owners of that particular policy type, right? So obviously my question semantically could easily match multiple different policy types, but the fact that I have structured data that tells me that the particular person using the website is an owner of, a home and contents policy, then that will give us, that additional context for matching them to that product. The other thing is, if you're using just direct LLMs, you lack explainability, right? Like, so what was the context that we used to actually provide the answer back to the original asker, right? With the graph, we can actually take all of the context of the chain of the graph that we use, like, so take all of the query that, the results of the query that we got from calling into the graph, and then we can actually, inside of the persistent graph, we can actually point to each of the pieces of context that we use to answer the question. So if we go and analyze like the effectiveness of the question, like we have feedback from that from users, then we can go and look, we actually have explainability around like what pieces of information were actually used as part of that. So using that structured data in conjunction with the unstructured data gives us kind of that power. And of course, as I was saying, like vector similarity doesn't equal relevance, right? So the fact that I search for a product, what if I already own, one of the highest ranking products, right? It's pointless. I'm not going to advertise to somebody or recommend to somebody something that they already own. And so, relevance is what is really key here. All right, so how do we build applications using knowledge graphs? So first of all, we connect. So we take those siloed data sets, we bring them to a knowledge graph, and a really easy way to do that is with Neo4j. We have lots of adapters for Neo4j, lots of data integrations. We can take data directly from data frames in a Databricks environment, for example, and pull them into Neo4j and construct a graph from that. It's a very simple integration that we have. And then we enrich our graph data, and I'm going to talk a little bit later about graph data science, but we can actually take that sort of ground truth, that base data set that we've pulled in, and we can actually run data science algorithms over that, and we can enhance it. So essentially we can do sort of high level analysis over the entire data set and create new connections in the data that we didn't have before. And then we consume, so we use this knowledge graph to ground our responses and improve search relevance. And of course then we, like I was saying before, we can capture, right? So we can take the results that we've been using, so the actual query results, and we can capture the original question and the relevant information that we used to respond to it. And so Neo4j has been contributing to a bunch of things to help us accelerate this, right? So as I showed in my original diagram at the start, not only do we want to improve effectiveness of the application, but we also want to get back on that really sort of fast ramp, right? Get that productivity curve to spike back up. And so we have a bunch of integrations that help us with that, right? So we've been building LangChain integrations. So essentially you can take the vector capability that's built into Neo4j, you can use a LangChain module to access that, but then we've also augmented that so we can add a vector query to a GQL query in Neo4j and combine that into a single module, so you can basically replace a plain vector search with a vector search plus graph. And so integrating into these helps us sort of accelerate the development of these applications. We also have integrations for all of the models in Neo4j. So basically, if I want to do text embeddings, for example, I can integrate that directly into my GQL queries. So every time I add an instance of a product, for example, I can embed the description and create a vector index around it. And so all of these integrations help us build knowledge graphs really quickly and integrate unstructured data into them. And so narrowing down now onto just the topic of semantic search, this is kind of the semantic search journey that we see some of our customers taking. So they start off with a simple vector search, using either a vector database or a vector index. Pretty much, all databases now have introduced, some kind of vector capability. And so it's really sort of low-hanging fruit to go and grab some unstructured data from, part of your structured data set, and then just create text embeddings for that, and then index it with a vector index, and then start powering semantic search around that. But as I was saying before, that doesn't really leverage all the structured data we have, all this additional information we have, as part of the results of those searches. So what we can do is we can attach a knowledge graph to the vector search. So structured data, as I was showing before, with pieces of unstructured data tied into our structured data set. And then, we can make queries that leverage both the unstructured data set and then reach into local graphs using traversals. And then on top of that, we can take a high-level look at the data set, run some graph data science algorithms, create new types of connections, and leverage those as well to make things like product recommendations or find relevant information to return to a user. And so we have components for all three of these kind of pieces of the path. Obviously, we have vector search built into Neo4j, and Neo4j, of course, is a graph database, so we have knowledge graphs built in, and we can do very efficient, very performant traversal type queries to back and augment those semantic search features. And then, of course, we have a graph data science piece of the product as well, where we can look at a live data set, project it into memory in real time, and then run data science algorithms across the top of it, and then generate new features and new connections from that, from those algorithms directly on that live data. And so I think rather than just talk about it, I'll show you some real examples. By the way, this example is based on a workshop that we give. We give this periodically in person at Neo4j. We also do it, in a webinar format. So take a look out for our events if you want to come and actually get hands-on with this stuff. I'll show you some pieces. But I'm also going to share the complete Git repo for this as well, right? So you can take this sample data set, pull it into Neo4j, and then play around with it and, do some of the things I'm going to go through here as well. And so this data set is really simple. There's an open source data set on Kaggle from H&M. Some of you may have seen it before. It's a good data set for, trying to build applications that do product recommendations. And so, in fact, it is kind of similar to data sets that, we would see at customers. Like, it's kind of siloed data, right? They have a nice product catalog. That product catalog has articles, which are variants of a particular product. The product has descriptions. The products are from departments. But then we also have our customer data. So we know which customers purchased which articles. So now we know a customer who purchased an article has purchased a product, right? Because it's a variant of a product. And so these are kind of two flat data sets that we've constructed together in a graph. And this is really typical of how you build a knowledge graph, right? You have this data, you just may not have, constructed it or brought it together into a single knowledge graph before. And so, yeah, this data set's freely available and you can bring it down. And of course, we can take these product nodes. So in Neo4j, we would add the product as a node. And each of these products has a text-based description, right? So it talks about, it's a jumper or a pair of jeans or something like that. And it has a very long-winded description of the product. So we can take that and we can embed it, right? So we just use a text embedding algorithm. And like I was saying before, Neo4j has, a plugin and a wrapper to allow you to take any piece of text or any piece of unstructured data that you have stored on a node, embed it with an API call essentially of your choice, right? So you give your API credentials and things like that to the configuration of Neo4j, and it will automatically take that data, embed it, add it as an instance in Neo4j as a node, and then add it to the vector index that's established on that field. And so it's a very smooth workflow to take this structured data of customers purchasing things, but then take this unstructured data of product descriptions and adding them to a vector index. So then we can, go via that vector index, with a product search or something like that to get to a result for the customer. And so if I have the really simple use case of a customer logging into their account at H&M and then doing a search for, a sweater or a pair of jeans, right? Very simple use case. So my initial thought there might be I might just implement that with a pure vector approach, right? So I just take whatever their search term is, embed that with the same model that I use to embed the descriptions, and then I basically do a similarity search with the vector index, and that will give me results, right? And in Neo4j, these results would look like this. There'd be a bunch of product nodes that vector search would come back with, and it would show you, a bunch of, pretty good candidates for the search terms that you requested. And in LangChain, that would look like this, like very, very simple piece of code because Neo4j has already, embedded everything and it's already added it to the vector index. We would just need to create a simple vector module in LangChain, make that module aware of the Neo4j connection details, and then we can basically just start asking questions. So it knows about the index, it knows what field has been indexed, and it will get us back nodes as a result from that. And so creating the index, and of course this is kind of the result you would get, right? What we expected. If we search, for example, oversized sweater, language models are really good at taking search terms like that and then, relating them to things like if there was a jumper or a pullover or something like that. It understands the semantic similarity of those terms. But what it doesn't understand is who was the requester, right? Which customer was asking for this, right? So if I'm a customer and I search for that oversized sweater, sure, it can show me 10 sweaters, right? And you can see all of these are pretty good candidates. They have really good similarity scores, right? So they're all much of a muchness. But which one should I show? Like which particular sweater should I put at the top of the search results? It really doesn't really matter, right, in this context, right? Because we don't know about the customer here. We haven't looked into who the customer is. We don't know what the purchasing behavior of the customer is. So we could just show them any of these. And this is how a lot of semantic search would work, right? But what we can do is we can actually go and augment this with a graph traversal. right? So a very simple graph traversal. And in Neo4j, this is really straightforward. So essentially what we're going to do is we're going to take each of the products that match well semantically, right? So like that sort of top 10 products I just showed. And then we're going to go to that product node and we're going to start traversing into the graph. And what we're going to look for is somebody who has bought that product, who buys products that I have bought, right? So in other words, if I don't already own this thing, then I'm looking for people who have bought it, right? That also buys other things that I've bought, right? So in other words, I'm looking for people a bit like me who have bought this product, but I have not, right? And then what I want to do is like do some maths essentially. So this is the way that I would implement that. And again, this piece of code here, we can just rip out the last piece of LangChain code that I showed, and we can just plug this back in. The rest of the application won't know any different. But what we're doing is we're slightly augmenting this vector search by adding a very small piece of GQL, right? So this GQL query, you can see GQL is super simple. Essentially what you have to do is just describe the pattern of what you're looking for in kind of this ASCII art format. So like I said before, take the results of that vector search. For each of those products in the results, go and find some articles that were purchased by customers who have also purchased articles that the requesting customer owns, right? And that's what that multi-hop query that I've highlighted on this slide is actually doing. It's looking for people who have bought things like me and then have also bought the things that have been recommended by the vector results, right? And so we can do that extremely quickly in Neo4j, right? So this, if you think about this, if this is a very large retailer, lots of customer purchases and things going on, the reason we can do it so fast in Neo4j is these traversals are kind of like pointer hops, right? Like we're doing this in memory really quickly. They're not like index lookups in a relational database where we have to go, 5 degrees of separation by doing recursive kind of joins and, big tree lookups and things like that. These can be done extremely quickly. And we're also not looking through everybody else's data. We're looking through only the data of this particular customer. So this query is actually anchored by that customer that has made the search query. And it's actually traversing out into the graph, looking for that article, but only related to customers who have bought similar things to us, right? And so this is extremely powerful and is only just this essentially the crux of this is 3 lines of code. And then all we do is we say, if we find, given the number of those occurrences that we find, right? So the number of products that we can find that link us to one of these search results through another customer that buys things similar to us, we just take that score and multiply the original vector score by that, right? And what that does is it boosts things that we've found like lots of similarity for, right? By looking into our graph. And so essentially what the results are for this particular data set is the 7th, this is what this last column sort of talks about here, is the 7th highest, vector only rank was the only one that actually exists in, this outcome here, right? So we found other products that we are more likely to buy than the ones that were in the top 10 that we showed on the previous slide, all right? And so the one that's, the common one here is rank number 3 now, is rank number 7 in the original vector search. But this particular product and the ones above it are something that is more likely to be purchased by this particular searcher because, people like this searcher who have bought other items like them have also purchased these products. And so that's a really nice, I think, example of creating this, marrying these two structured and unstructured data sets, using the language model for what it's good for, which is getting us close to a set of products, but then evaluating those products against structured data that we have about the customer, right? Okay, so I also promised that I was going to show an example of, what sort of things can we derive generally from the graph, right? So let's take a zoom back, think not just about this customer, but generally about purchasing behavior of all customers across all products, right? And that's what the data science piece in Neo4j allows you to do. It allows you to sort of take this, a cut of the data, so a slice of the data, take a pattern, just project that pattern up into memory, and then that will create this ephemeral graph, right? This ephemeral in-memory graph of just things that I want to focus on, and then I can run algorithms across just that ephemeral graph, and then I can produce outputs, so I can produce outputs embedding scores, or I can produce outputs like new relationships that connect things together. And that's generally, I mean, it's quite a long topic that we don't have time to dig deeply into today, but that's generally what that piece of the product is designed to do. And so the example I'm going to show here is what we did is we just took articles, right? So again, this is another cipher pattern that I was talking about, a GQL pattern, where I have articles, right, which are purchased by a customer, where a customer also purchased another article. So if you look at these two variables in this match statement, A1 and A2, they're things that are bought together, right? So it doesn't matter who bought them, but they were bought together. So there are customers out there that own these two things, right? And so we can create this really simple projected graph called a co-purchase graph, right? So things that are often bought together, right? And so that itself is this graph of, products just connected together. So you can see that I've taken my original graph, which is about customer and purchase data and things like that, and I've projected it into this new sort of summarized graph of things that are bought together, right? Which is a really rich, digested sort of graph. And then what I can do is I can run an embedding algorithm called FastRP, and essentially what that does is it looks at those products and the things they're connected to, and it creates an embedding from that. So an embedding is essentially a lower dimensional representation of a node in a graph, right, based on the connections it has to other nodes in the graph, right? So it's just like a text embedding, but it's a text embedding for graph data, right? And what we could do is we can then use like nearest neighbors to say what products are similar. So in other words, if this product is often bought with this range of products and this product is often bought with a similar range, like maybe a good overlap, then they would be similar in the embedding space. And then we can connect those two products together. So what we're doing here is generating a new customers also like relationship. And so this is actually creating a new layer in our graph, right? A complete new layer. So you have like the truth layer, which is just like what people are buying, but now you have a layer which is connecting products directly with customers also like relationships. And so I can use that in a number of ways, right? That's really interesting information. Like I have a graph like this now that if I'm sitting in a product, I can take that product and produce a list of products that on the whole, customers also like. And so there's lots of different ways I can use this. I can take the customer, look at the products they own, and then look at the list of, for each of those products, look at the list of things that are generated from the customers also like relationship, and these are really good recommendations. But then I can take that list and I can actually match it against my original vector search list, right? So it's like, so now I'm a customer, I'm trying to predict what I would like to buy, but if I take my search term and I do a vector search on it, I look at the results of that original piece of the search, and then I do sort of an intersection on the things that a typical customer like me would be buying, and there is a common result in there, then this is a really good hit, right? It's something I'm likely to buy based on the corpus of transactions, plus it's a good search match for my original query, right? So again, I'm marrying this concept of mincing up this like general purchase behavior of all the customers, but then I'm combining that with this this motion of vector search. To pinpoint exactly, because again, like as I showed in the original vector search, it was really a toss-up of which one to show to them, right? But this can help us nail down exactly which item we should bring to the top. And there's other uses for this, this new generated graph as well. Like, so for example, if I take an item and put it in my basket, right? So I've done my vector search, we've done our graph traversal, we've promoted things to the top of the list, and I've decided, yes, I'm going to buy that and put it in my basket. I can now take that item and run that same traversal query across that customers also like, and now I've got recommendations for other things that you might like to add, right? And they might be socks and jeans and things like that. They could come from anywhere, right? Because we're not doing that intersection between those two data sets. They can be from any department. So yeah, a really nice way to generate not only recommendations from specific search terms, but more general recommendations as well from the corpus of purchase history. Okay, so if that's interesting, I think I sort of covered a lot of ground there. And this is like literally scratching the surface of what knowledge graphs are capable of. Then I just want to show you a few things. There's lots of QR codes here, so if you want to bring out your phones and scan these QR, if you don't get them all, it's okay because we have most of these at the booth as well. So if you come over, we have like little cards that have QR codes on them as well, and you can get to most of this. So this set of examples that I show comes from a workshop, and the entire Git repo is right here as well. So you can go here, you can create an Aura instance. Aura is our managed database service, so it's a managed graph platform. And then you can actually just use Colab to run some of the code that I showed here in the examples. Some of the tooling that I talked about, like LangChain modules, and things like that. We also have some tooling around building graphs. So when I said, you can take a graph model, point at a piece of unstructured data, and then have nodes and relationships on the basis of that graph model generated from the unstructured data. We call that the graph builder. So we have pieces of that in the ecosystem as well. That can all be found here in this particular labs page as well. So you can go there and look at all the pieces of the Gen AI ecosystem that we've contributed to. We also have a Graph Academy, so we have a whole online learning platform as well. So if you're interested in taking courses on even going from the basics of graph, I know I didn't cover any of that, and I apologize for not doing too much of the backstory here, but that's all on our learning platform, so you can go to Graph Academy and learn that. And we also have a course around knowledge graphs and generative AI live on deep learning AI as well, right? So this is obviously a popular learning. Famous Stanford professor here opening for the course. And, this is a really great course which teaches you just what you need to know about property graphs and knowledge graphs, just enough to start building Gen AI applications, and then, some of the similar concepts that I've described today as well. We also have an online developer conference. I know this is a lot. So starting November 7, we'll have lots and lots of sessions. This is all available online for free, so you can basically join this conference and learn lots. And I mean, this will be not only Gen AI and language models, this will be across all graph use cases. So some of those use cases I talked about at the start, they'll be represented in this conference also. All right, that's all I have. We are going to be outside as well, so if you have, if this has sort of struck any thoughts for you and you have some use cases around this sort of stuff that you'd like to talk about, come and see us. Otherwise, sorry to keep you a little bit over time. But yeah, hope that was useful. Thank you. So.